and welcome back. What we were discussing is that we formed in the entire pattern of genetic algorithms, how they eventually evolve out any system, how they eventually optimize, and what I get as the end product is the best kind of system that I can formulate based on any kind of technique, what is sometimes referred to as the non-problem specific technique. I did not make any specific assumption that I had some kind of gradient with me, I had some kind of function with me. I knew internally what the problem domain was, but eventually I can, by minor crossover, by some minor modification, I can get is that the highly optimized individual to solve the problem. And we discussed in that there would be some kind of problem where the fitness landscape would have some characteristic nature in which there is a possibility that the algorithm behaves in such a way that the various individuals, they get trapped and they get converged in some kind of a local minima, and when they converge in some kind of local minima, even the mutation will not be able to get it out of it. So we devised a technique called as diversity preservation, a concept which said that please preserve your diversity. A very premature version of it might say that the separation must be less than some threshold eta, and then based on that I can say that if it's less than eta, then only the crossover would be allowed. So many times what we even do is that just to find out how the fitness landscape is, we say we start off with some 100 individuals, and what we said is that we apply the genetic algorithm with this concept of diversity preservation, and after that we, let's say, get in a number of local minimas entirely in this fitness landscape. So it's like we apply a strong kind of fitness landscape diversity preservation technique, and sometimes what eventually happens out is that we can get 100 local minimas that are spread all around the fitness landscape. So this can be very, diversity preservation can even be a very good tool if I have to find out how my fitness landscape is. And when I'm trying to say, when I'm trying to state how is it that my fitness landscape is behaving. So I need to get the various local optimas, the local minimas. In case of a cost landscape, in case of a fitness landscape, the maximas. So I need to get in multiple optimas spread right across my fitness landscape, and then is when I say that based on their distances between them, based on their minima value, I can get an idea of how the fitness landscape is. Because if the problem was to minimize, let me say if my cost landscape in such a sense is something like this. Now this is what happens to be a global minima, and this requires some kind of machine specifications, but let me say that the evolved machine was something that happened to have this kind of specification, but then practically I might not be able to work out this machine because human error will range anywhere between a plus delta to a minus delta. There will be some human error, and that is how the value of it deteriorates extensively. So this kind of machine that I am trying to produce, because of some kind of induced machine error, human errors, I might not be able to produce, and I might be actually interested in this kind of minima, wherein even if I make in some kind of errors, I'll still have a fine fitness value. Now it's better to have this fitness value than to be in this region over here, what this to represent. So that is what is known as a robust genetic algorithm, and many invariants that you can eventually build using the same technique. Many invariants that you can actually imagine out the same. What this R we are supposed to deal with is another interesting topic that plays a big role in the analysis of the algorithm. I call it as the schema theory. Let me say the individual that I had was a bit string representation. So I had a long list of zeros and ones that ultimately made up these solutions. This was my one individual. I had an entire population of it. What I am trying to find out is that by a simple flipping of these bits, is that can I get something that is the most optimal in nature? Can I get an optimal set of parameters where parameters are nothing but these bits, and these bits can only take in values of either 0 or 1. And of course I have a fitness function to find out what exactly this fitness value is, and based on all those techniques I'll get an interpretation value and apply selection, mutation, crossover and all those things. So I make in a fitness landscape of this kind of thing. I make it a fitness landscape of exactly this genotypic representation or the bit string representation. What I get is again a multiple dimensional space. Let me say that this n is the number of bits over here. I had earlier taken in problems like, based on this I had to optimize this. I said that 10 bits for this, I said 15 bits for this and 25 bits for this. So this will be some 50-bit representation over here. So this will ultimately be very, very dimensional in nature. And of course my vertical axis would be the fitness value. Let me say I only draw 3 of these dimensions, the other exist, but they are not drawn. Now all these are bound between 0 and 1. 0 is the minimum value and 1 is the maximum value, so I get something like this. Again, for all combination of zeros and ones, I locate the space in this surface. I plotted this fitness value vertically and I get some kind of fitness landscape. I get in some kind of fitness landscape that is prevalent over here. And it can be imagined how complex that would be because the space is highly dimensional, firstly. And secondly, only this position is possible, only this position is possible, only this position is possible, and only this position is possible. So I'll get in a very discrete kind of fitness landscape over here. I cannot have something like 0.1, 0.2, 0.3. Either I can have 0 over here or 1 over here, 0 over here, 1 over here. So this would be a simple architecture. What I again draw out is the space over here where only the surface is drawn. I say let me drop out this axis and let me draw only the surface, similar to that we had done in a genotypic representation with double vector representation in the previous fitness landscape that we drew, where we had all sorts of analysis over it. So this would be something of the form. If I draw out this over here, it would be something in this format. I'll have to make in this kind of a cube over here. So this would be what it would all be about, and this would be the 3 axis. Let's say the x-axis, let me say this was the y-axis, let me say this is the z-axis, this is the point 111, this is the point 000. All the 8 locations are possible. So these are 8 locations possible when I make it in 3 degree. If I make it a 4 degree graph, there will be 16 locations possible based on all these combinations of zeros and ones. Unfortunately here again I cannot draw more than 3 dimensions. What this is known as a hypercube that spans across n dimensions, where n is the length of the bit string representation. And of course the point is finding out the best point over here and finding out the best point in this hypercube. That is what we are supposed to do in this highly dimensional hypercube. So this is what the fitness landscape in this case would be. Now normally it's of course impossible to analyze these kinds of landscape. That's why we always analyze landscape in the phenotypic representation or in the genotypic representation, double vector representation as we drew up in the previous case. But let me go apart from these fitness landscapes. Let me introduce a term known as a schema. A schema is nothing but a template that is a representation of an entire population. So let me say my schema would have in n bits, where n is the same the number of bits in any one individual of this population. N is nothing but the number of bits in any one individual of this population. So let me say that my schema will again have n bits over here. Any bit, so let's say the schema will maybe represented by x. So any bit xi can either be 0, it can be 1, or it can be star. Any bit in the schema can be either 0, 1 or star. It will be 0 if all individuals have 0 at ith location. It will be 1 if all individuals have 1 at ith location. It will be star otherwise. So I had a population of individuals S1, S2, S3, S4, S5 and so on. This population P will have a schema X. It will have a schema X. X is of the form x1, x2 up till xn. What I say is that I start off with the leftmost bit. I see is that all the individuals of this population have got a 0 at the first location. Is it that all the individuals have in 0 at the first location? If yes, I write down 0 at this bit. Otherwise, I ask, is it that all the individuals of this population have got 1 at this position? If yes, I again write down 1 at this location. And if some of them have zeros and some of them have 1s, if all of them except 1 has 0 and 1 has 1, if all of them except 1 has 1 and 1 has 0, so any combination of bits, then I say star. Star means that all the individuals neither have 0 nor have 1 and there is a mix between them. So based on that, for any population P, I can assign a schema. Based on any population P, I can assign a schema to that population. A schema is a template that tells me approximately how individuals inside that population are. A schema to a population is a general kind of template that tells me how are the average individuals inside that population. So let me say is that if I continue the evolution process, if I by chance happen to continue the evolution process, how is it that my schema will change along with time? How is it that my schema will change? So let me initially start off with a very initial schema that would be there. At the first generation, my schema is nothing but a collection of stars. Because let me take let's say the fifth bit over here. It's a random initial population generation. So out of 100 individuals that let me say was the size of the population, approximately 50 of them would have zeros over there and 50 of them would have 1 over there. Approximately 50 of them would have 0 and the other 50 would have 1. So there's a mix between 1s and zeros. That's why I say it's star, and that would be true for all the positions over here. So this is what my initial schema would be at any time. Let's say generation 1 up to generation 2, 3 and 4. Let me say the schema remains the same, but eventually what would happen is that a few bits will change. This means that these bits have attained their value. They have attained some kind of value. So So when I have this kind of schema, I know all the individuals in their second location have got 1 and all the individuals at their third last position have got 0. Now again remember what has happened is that now because all the individuals have got 1 at their second location and 0 at their third last position, I do not need to work over these 2 bits. I do not need to work over these 2 bits. In my double vector representation, I said that all that will happen is that the type of surface that exists around the existing individuals of a population, I only work around that surface. So that's when I said there happens to be something like this. All these some kinds of solutions, and I said that I will not cross this, I work inside this. What has happened is that 2 individuals have already got their positions. So all individuals have 1 over here and 0 over here. So I will not work outside the space, I work inside the space. So I might not visit these 2 bits. Of course, that's only because of crossover that this thing was happening. Mutation had some parts that it could expand the search space. So because of mutation, of course, they might get replaced. And of course, again, because crossover is much more dominant than mutation, so I assume that these 2 bits have been fixed, they will not change. So eventually 2 bits have been placed over here. What it means in our hypercube is that earlier the dimension of this hypercube was n. Now this hypercube has been streamlined to another hypercube of dimension n minus 2. Now I need not consider 2 dimensions, I have only crossed out 2 dimensions in this hypercube. In my fitness landscape again the same thing happens. So this is some kind of contraction that is similar to contraction that we saw in the double vector representation. The only difference is here we are contracting dimensions, here we are reducing dimensions. As we go on, we will keep on reducing the dimensions. As we go on, the number of dimensions will eventually reduce because of this schema that we have got. Let me further go at any, let's say 50th generation, the schema would be something like 1 1 star 0 star star 1 1 and so on till star 0 star 1. This will be 0. Again, if we go on, finally what will happen is that the entire schema will have a couple of stars and the others would be all numbers over here. So again, it can be seen is that there is some kind of convergence that is happening, convergence in terms of the dimensions getting reduced. And as we had in our double vector representation, I want to repeat the same discussion again, that there was some kind of diversity that was always existing because of the mutation operator depending upon the mutation rate. They all did not converge at one point of time. The best witness was never equal to the worst witness because the moment that gets equal, mutation operator does some kind of tweak. It does some kind of exploration. It pushes out that individual. So that's why you see some effect over here. And of course, that is like a very small subspace to work with. So towards the end, I'll get almost my entire schema as a collection of numbers, and that is my final optimized individual. That is the final individual. That is the optimized individual. So into this hypercube, it can be seen that as we go on, dimensions they keep getting reduced. In my fitness landscape, it can be seen that the dimensions keep reducing. And in my schema theory, it can be seen that the stars they get reduced and they get replaced either by 0 or 1, depending upon where is the local optima located. Now here we will not touch up how diversity preservation plays a role here. The exact discussion is entirely the same, where I get multiple schemas being optimized and then ultimately converging to one kind of schema. What is important to discuss is why is it that these stars are getting replaced by 0 or 1. And that's again because of the theory of the selection of the fittest, survival of the fittest, the Darwinian principle that comes into play over here. Let me say if there was a 0 over here in this place, those individuals had extremely bad fitness value. As a result, they could never get selected. And because they could never get selected, they got extinct. And we had only individuals with 1 year that could survive this population. Similarly, if there was a 1 here, let me again say that those individuals, they had very bad fitness value and they ultimately got extinct. They ultimately got deleted, they ultimately got vanished off, and only those individuals survived that had 0 over here. Those individuals that have 1 over here and 0 over here, they would have some higher amount of fitness than the average individuals. They would have some higher fitness as compared to the average individuals. So therefore, any kind of mutation, elite or crossover that they participate in, those individuals will again have 0 and 1 over here. So this kind of basic instinct of having 1 here and 0 here, they will not keep this characteristic with themselves, they will keep passing this characteristic to all the various individuals that they interact with. And as a result, this characteristic of having 1 here and 0 here, it will increase to such extent that ultimately only those individuals will survive that will have 1 here and 0 here, and that is when the schema will change. So let me say that 4 generations were needed to pass on this characteristics, to have this characteristics multiply, to have the other individuals being deleted from the population, and these individuals with these characteristics being multiplied. After 4 generations, what happens is that the entire population that had 0 over here or 1 over here, it got entirely extinct. And then is where we got this kind of schema that you see over here. Now again, let me come to this 1 over here and 0 over here. We've seen that there would be this kind of division, there would be this kind of change that would be possible because of the Darwinian principles. Let me say that there's something known as the ease of optimization that every bit has. There's some kind of ease of optimization that every bit has. Now imagine that you are living in a world, again I'm taking the same human kind of analogy. Imagine that you are living in some kind of world, and in this world some characteristic is very bad. So sorry again, a technical disturbance, so many features disturbing it. But anyway, so we were discussing that there is some kind of ease that every bit has for its optimization, and what we were discussing is that, let me again go into the biological analogy of the humans, that there is a task for which the tall height is very bad. It's extremely bad characteristic that you can have. So let me say the task was going in a small kind of place, and therefore people who had big heights, they could very badly do that amount of work. Now as a result that happened, what happens is that all those people who had big heights, they showcase very bad fitness value. They showcase very bad fitness value. No longer they had, no wonder they had very good other characteristics, strength, build, fairness, all those things. But because of this height, they performed very bad. On the other hand, those individuals that had poor height, they could perform the task very well, even though they may not have that good other characteristics. So if we have a look, there can be a straight demarcation that can be drawn, is that those individuals that have got big height, they cannot perform this task, and those individuals who have got in small heights, they can perform this task very well. If you make this a rule, if you make this as a hard-coded rule, and try to find out how many individuals they satisfy this rule, you will get a very high number. You will get almost 90 to 95% accuracy in this rule, because those who were tall, they were not able to do it, and therefore all those characteristics that combine to height, they very easily be optimized. They very easily get to their locations out here. Those who best that are responsible for height, they automatically taken their optimized value very early in this optimization process. Now from here when we move on, it's like saying that those individuals that have got good height is already fixed, that is small height now. Then we try to work over the other parameters, and of course those are not as easy to work upon. So every bit has in some kind of ease of optimization, or the standard term as such, and that represents the kind of generations it takes for this bit to be optimized. Those bits bits that take the optimized value very early will be the ones that are very easy to optimize. Those which take late, they are slightly more difficult to optimize, and the other are very, very difficult to optimize. Again, what this denotes over here is that the presence of a 1 over here, the presence of some kind of 1 over here was very, very likely for the individuals. If I change this 1 to 0, the average fitness of my population would drastically reduce. So let me say by chance if I fix this as 1 over here and generate some kind of individuals, those would have very high fitness value, and for the same individuals, if I change this 1 to 0, those will have very, very poor fitness value. This will not be there for any other bit. So every bit represents some kind of characteristic, that some kind of ease in which it is able to take a position from start either 0 or 1 in this evolutionary process when we consider this schema. Of course, we will not go more into this kind of schema thing. We will not touch upon the entire intrinsic factors within, but then the motivation is just that as we go upon more and more, what will happen is that every star being converted into a 0 or being converted into a 1. Let me take a very general example as such. If I said my optimization is nothing but fx equals to x square plus y square, x lies between some lower bound and upper bound, let me say minus 10 to 10 and y between minus 10 to 10. I need to, let's say, maximize it because I'm using the word fitness over here. What would eventually happen out is that the locations around 10 and minus 10 are very likely for this over here. Let me say that x was represented by 15 bits and y was represented by 15 bits, and those were the 15 bits over here. I'll have to take this as a minimum. Let me say this was a cost function where the cost was minimized, so locations around 0 are very likely over here and locations around 0 are very likely over here, and those are some 30 bits. The first 15 representing x and the next 15 representing y. What would eventually happen out to be is that the bits would be arranged in such a format that those around 0 would be promoted, so all the higher bits are unlikely. These all will start taking up values from 0 from here on and from 0 from here on, and the other bits would naturally coordinate. I am assuming that there was no sign bit over here. If there is a sign bit, you will have to arrange for naturally. The sign bit will take time to evolve because point 1 and plus and point 1 and minus, it has the same fitness value. So the sign bit, if it is present here, it will take time. But eventually out, these bits, if I change this to 1, it means a very high value. If I change this to 0, it means a very low value. If I change this to 1, a very high value means this function will take in a very high value. That is what I want. If I change this to 0 over here, a 0 over here, that is what I eventually want. So the most significant bit over here would be the most easy to optimize, and the most significant bit over here would be again most easy to optimize. Again, if I change the most significant bit from 0 to 1, let me say I can vary from 1 and after that 14 zeros to 1 after that 14 months. This is the maximum that I can get, this is the minimum I can get. This represents some very high values of x and y. X over here, and similarly I can take for y over here. And on the other hand, if I vary from 0, I get my absolute minima. That is a value of 0 over here to a decent value. This value is decent enough if I can play around with this, and in fact this is a value that is smaller than this value. So if I change this bit from 1 to 0, the maximum that I can get with this bit having been 0 is smaller number than what I can get from this being set to 1. and therefore it is very simple to optimize the most significant bits over here. Again, most of my discussion was assuming that there is no sign bit, so I can eventually say this was my number. I assumed somewhere that there was no sign bit, so this is what I basically worked upon. The most significant bit would be very easy to optimize. First, these two will take their 0 over here and 0 over here, the rest all stars. Because again, if I change any one of them to 1, my number that it represents, it shoots up like anything. Then these two will get 0, because again I am dealing with the numbers that have only 0 at the most significant bits. So that dimension is over now. My workspace has been reduced. In the reduced workspace, the second most significant bit carries a large value. If that gains 1, x will have a very large value, and that's why x square plus y square will again have a very large value. That will be surprisingly higher than what would have been the case when it would have been 0. And so on, it will keep on optimizing until the entire bit string is 0. So that was a very basic kind of treatment into what the schemata theory is more or less about. We study up what has been left from a long time now. What about the infeasible solutions? What do I do with them? Because it's infeasible solution, I cannot calculate a fitness value by any conventional method. At this point of time, I won't say you call this function as a fitness function, but I can say I cannot find out how good they are in solving the problem by any method, because they cannot solve the problem. Infeasible solutions are those solutions that are not able to solve the problem because of the constraints that they violate. So I need to do something. There are multiple ways in which that I can handle. The first is, say, delete and replace. A very simple technique. If I had a solution that wasn't following a constraint, I simply say delete this individual, delete it up altogether, and replace it up by another individual that is random in nature, but then that has some kind of constraints. Again, not a good thing to do. Because towards the end, if I get any kind of such scenario, in which an infeasible solution happens to be generated at the later stage of time, it will be replaced by a random individual, and that is acceptable. That should be acceptable. But what happens is that out of a population of n by 2 individuals, they get infeasible. Infeasibility is up to that high extent. I'll have half of my population random and no convergence at all. I'll have no kind of convergence that I have in my algorithm. And convergence is what I really need to have. All individuals concentrating upon areas around what is perceived as the global minimum. So again, find technique when the solutions are, the infeasibility is less likely to be produced in individuals and unlikely otherwise. Again, how easy it is to replace it with a feasible solution. I generate random numbers and those again happen to be infeasible. So again, I will have to replace them again and again till I get a feasible solution. The problems are so hard that half of the problem is finding out the feasible solution, and once you've got any 1, 2, 3 or let's say 5 or 10 feasible solutions, then you can work over them. They're so hard to solve. If you generate 1,000 random individuals, only let's say some 20 of them are feasible. So again, it will not work in those scenarios. But again, the find technique as such, I can simply say that assign lowest fitness or the highest cost. Fair enough. I say that minus infinity was the lowest fitness possible that my system could have. I said let this fitness be assigned to that individuals. So in this case, my fitness function is nothing but the fitness of any individual S is equal to its utility if individual is feasible and minus infinity if it's infeasible. And fair enough system. Why fair enough? Because we know that next time there will be something known as survival of the fittest, and this individual would automatically die. It will be replaced by a new individual, and that again is fair enough. But again, what happens is that if half of the population has this kind of problem, half of the population is infeasible, and therefore selection or survival of the fittest will have to select these individuals. It has no choice rather than to select the bad individuals, and those are really bad. So then the number of infeasible solution of fair enough, you can have any of these two techniques. This of course will not, when the convergence has already taken place, this method could produce some kind of individual outside at a random location that would have affected either positively or negatively. This will not have those effects where after convergence also the individuals would die, and based on the fitter individual the convergence limb would be formed. Third, I say is repair. Very good operator, very well used. You have bad individuals, you try to repair it up. You try to convert a infeasible solution to a feasible solution. So what I get is that if S was my individual, I simply say repair S, and I get my new S over here. So that's what the repair operator does. And this is again a very handy operator, is that because I can map any infeasible solution to its closest feasible solution. I can handle any kind of infeasible solution to its closest feasible solution, and as a result I am safe. I need to only work up with my algorithm. I need to only work up with what I have to do. Irrespective of my solutions, I can be damn sure my solutions are always feasible in nature, and that's what gives me a very big hand while I work with these kinds of solutions. Whenever I do the fitness landscape, I always have some smooth lines. Now we know the smoother the better, the more easier. What this does is that it tries to have the strongest correspondence that the fitness landscape is fine, because having infeasible solution would have had steep walls over here, assigning the highest fitness value. Delete and repair would have replaced it entirely with something new. You do not know. So repair is safer in that sense. It maintains the fitness landscape. Penalize. Repair is fine when there's a bulk of infeasible solution as well. It will again do some kind of mapping, and even if half of the population is infeasible, that will be work. But then again, the big question is that what if my problem is that generation of a feasible solution is itself a big problem? It is very difficult to generate any kind of feasible solution. And because it is very difficult to generate some kind of feasible solution, what ultimately happens is that it is very difficult to work upon. So in such situation, even repair would generate more or less random individuals. That is perhaps true. Of course, it would be more deterministic in nature in the kind of solution that is generating. They might have predictable feasible values for better fitness values. But what I do it out in penalize is that I say that my fitness of the individual S is equal to nothing but its utility in solving the problem. Let me say some amount of, I could measure it approximately, plus alpha times the amount by which it disobeys constraints. This alpha is called as the penalty constant. So what I want to try to do is that I say that I could get some kind of utility that the solution may provide. I had a solution was infeasible. I could measure some kind of utility it could probably provide. Had it been feasible, I assume it to be feasible, calculate this utility, but then I apply some kind of penalty to it. I am subtracting its fitness. I am applying some kind of penalty based on the amount to which it could not obey the constraints applicable. It could not disobey the constraints applicable. So let me say if my problem was fx, comma y equals to x square plus y square, and for my problem x minus y had to be less than 3, x varying from 0 to 10, y varying from 0 to 10. If I have any solution, let's say x1 y1, which is an infeasible solution, So all I say is that my fitness value of the solution x comma y, x1 y1 will be equal to x1 square plus y1 square, its utility, minus, let me say the solution was to maximize this, minus a minus over here, some constant, and the amount by which it is disobeying this constraint. So the amount by which it is disobeying this constraint is nothing but a magnitude of x minus y minus 3. So this will act as a kind of penalty to it. So what the algorithm ultimately try to do is that it will try to reduce this penalty as much as possible. It's an genetic optimization tool. They try to increase the fitness. To increase the fitness, they try to reduce this penalty as much as possible and to increase the utility as much as possible. And eventually, penalty will get reduced to nothing. Eventually, it will happen. Penalty will get reduced to zero. That's how I will get some solutions in hand that will obey all the constraints. The penalty will be zero, and once the penalty will be zero, it only has got the task to maximize the utility value. So that's again a general kind of technique by which you can handle out the infeasible solutions. Some again random points of discussion at this stage of time. I can have some kind of adaptation in parameters. What happens is that in my fitness landscape at group, all the convergence had happened. And mutation was trying to move it over places again by very, very small amount. At this point of time, I would like to reduce the crossover rate and increase the mutation rate. There is no point in going up with these small movements. So what I will try to do is that try to decrease the crossover, try to increase the mutation so that I have more dynamism into the system. So something in which you can try to measure the diversity, try to measure how the convergence is not as holding, or try to adapt to these parameters up to this value. After a long time, this would be the solution. The mutation will dominate crossover. Now I will try to reduce the mutation rate and increase the crossover. I would like some kind of convergence to happen. So let me say now my convergence is somewhere around here, where the global minima was somewhere around here. So many times we use such kind of technique. We've got only some amount of time to play around with. Many times what we would do is that if I have this kind of technique, I'll try to generate out new individuals. That is what was the insert operator that we do. That we'll try to judge whether random places are good or not. There is more good use in having the working over this converged values. Of course, in some applications is of use where you actually need the minima values. In some applications, you are not concerned whether the answer was 0.001 or 0.001. That difference also make you. What you would like is that whether it's possible to get -1 or -2. So we would like to explore new places by some kind of insert operator. So again, numerous ways in which we work around with all these kinds of operators. The actual adaptation, of course, we take in a separate as such, where we try to fix in these values. We will see later into the evolution strategies how they are able to do it. So the actual word adaptation is not being dealt as of now. Many times what is done is that if this is the landscape, at any time these are the individuals, I select some good fitness individuals scattered around in the fitness landscape. I call them as the females, the rest I call them as the males. And then I have a multi-parent 6 determined crossover, where this female intercourses with multiple males to generate multiple people, offsprings out here. This female will again generate multiple offsprings out here. They are all localized in nature. Now again, remember that when I say localized crossover, that means that individual only allowed to crossover with the neighboring. I mean it's a kind of diversity preservation. So some kind of diversity preservation also that this happens, and because I've already classified the individuals as male and females, the higher fitness value the females that are scattered all around, and the others labeling it the males. It is kind of sex determined kind of crossover that I apply. So numerous ways in which various adaptation varies invariants can be formed. We of course dealing with a smaller part of the entire, usually computing the other parts of it, we would be dealing after taking in some basics of the fuzzy logic and the fuzzy inference systems. What is again important to discuss, one of the last topics that I will be taking out over here, is that if I can have, what is it that the parameters are all about? What are the parameters of genetic algorithm and how do they behave? So I have got one thing that is known as the number of individuals. I have got something known as what we've already seen, the crossover rate, the mutation rate. I have something known as a stopping criterion. How do we fix the values of all of these? And of course I'll explain some about the probabilistic nature of these algorithms. Now usually what happens is that if I increase the number of individuals from 1 to 2, 2 to 3, 3 to 4, and n to n plus 1, if I start increasing the number of individuals, I go from a uni-agent or a single agent approach to a multi-agent approach. And because it's multi-agent approach, it has got a lot to do with parallelism. It has got a lot to do with escaping the local minima and getting into the global minima. Many people are able to search a minima much more easier than one individual is able to do. So if one individual gives me this kinds of trends, that is how the fitness increases along with time. Two individuals will be able to do it much better and they'll eventually lie off at the same place. This was one individual, she would be able to do still better. 10 would be able to do still better. And a high number, 100 would be able to do still better. Eventually you will see that after some amount of time, from increasing, now this is time, this is generation. This is what the curve would be. They all come out to the same value. Of course, one agent might get stuck at some local optima. That is why the trend may be like this, that this is indication of not getting into, this was what was the global minima and this was what was global minima. Might be 1 and 2 get stuck up over here, but eventually the higher generations will strike the global minima and that is what they will come across. They will not converge out at this point. This is what would be known as the point of the convergence, where they do not change in value. The convergence of 1000 is much more earlier than the convergence of 10. It's much more earlier than the convergence of 2, than the convergence of 1. And more than 1000 will show the same trend. So it's like the additional individuals are trying to add something new. But if we look at generating an algorithm that solves a problem with 1000 individuals will take a 1000 much amount of time than the same algorithm for one generation with a single individual. By adding individuals, I am trying to multiply the fitness evaluation needed. I am trying to more complexize the sorting algorithm that is inbuilt into the algorithm. And as a result, what would happen is that my algorithm will become slower with 1000 individuals. So if plotted with time, my 10 individual approach would be at the 100th generation. At the time, my 1000 individual approach would be only at its 10th generation. Because after taking using the system, you run an algorithm, so time is very important. How much time it takes? Difference between 1 hour and 10 hours is too much. You might wait for 1 hour to get the answer, you cannot wait for 10 hours. So based on that, many times what happens is that the fitness function is too time consuming. Many times the fitness function is too time consuming, and if the fitness function is too time consuming, what we eventually do is that The total number of calls you can make to the fitness function are limited in nature. Let's say one fitness evaluation takes 2 minutes. You can make for 2 hours, so you know the total number of calls to make in the fitness function. Those are limited. So in that case, if you increase the number of individuals, it will automatically mean you decrease the number of generations to get results within time. If you increase the number of individuals, you will have to decrease in the number of generations, and that is when higher individuals would mean working over with lower number of generations, and working over with lower number of generations would mean that each individual gets a chance to jump only a couple of steps. It doesn't get a chance to step up more. That is when the convergence is very low. Towards the end, in such a population, there are 1,000 individuals. They will be located like this. After, let's say, allow the generation, those were 10 in numbers, and that is like more or less random in nature. So increasing individuals in such a context would be adding randomness. If we keep only 5 or 6 individuals, after 10 generations, they would be nicely converged. After, let's say, allowed number of generation, that was 50, working out with 5 individuals, and with 1,000 individuals only, it was 10. As per the time constraints that we got. Towards the end, what we need, this convergence is very important. Whatever algorithm you work with, it needs to converge. Convergence is like when all the individuals, they are searching at the right place, the global minima. Effectively, all the time that you employ is spent out in searching the global minima and not the global minima. Now again, one individual, let's say only one individual over here with allowed 1,000 generation is again not good. It would converge, it would have very good convergence inside. All the time is consumed searching out in and around the minima, but that minima may be local minima. So this has got the problem of convergence at local minima. So again, that's how you need to decide the number of individuals nicely. Too many for fitness function with which are time consuming, too many individuals would be completely random in nature, and too less would be convergence at some local minima. The ideal number lies not too much and not too less. Again, I am changing the number of generations over here. So we're done with this. We've seen almost how the mutation and crossover lies. So normally the crossover rate will be higher than the mutation rate, it will be much higher than the mutation rate. So because of the same problem that towards the end we need all the individuals searching around some fitness landscape, searching for the local minima or for the global minima, and the individuals higher enough, so that means the convergence rate also cannot be that high that the convergence happens to be at some local minima, as we just saw. What is important is the probabilistic nature. It just states that if 10 people solve the same problem, if you solve this problem with the same algorithm, with the same kind of structure 10 times, it's probabilistic. You may get the same answer, you may not get the same answer. Sometimes it may converge because of wrong parameters to a global minima. With the same parameter at the other time, it may converge to a local minima. So all these things are possible. So whenever we work with such kind of algorithms, the intention is if we can run the algorithm numerous number of times and see if the average performance is good. You might be lucky enough that the initial population was generated, and by chance an individual already happened to be around the global minima. It was nicely enjoying its high fitness value there, but it may not happen always. The next time you run, it may be well diversified. So they are probabilistic in nature. We try to adapt the parameter in such a way so that the average performance of the algorithm for the number of runs is maximized, rather than we run the algorithm and straight away take whatever the final solution was as the actual solution that we got. Now that is being dependent on some kind of luck. There may be some, because it's probabilistic in nature, there is a possibility some luck playing a factor over there. What the stopping criterion says is that if you have already converged, no good in having and continuing this algorithm. No longer continuing this algorithm. That is where the stall generation and the stall time comes into play. Now even if you allow this algorithm to run for a number of times, it has already converged. So nothing good would happen with it right now. If it has not converged, it if the solution is like this, of course you may get advantage, so you may continue it. So this is how where the small generations come into play. The small generations will decide how the algorithm behaves. The store generation, of course, only this is decided on the basis of best individual. It is not decided on the basis of average individual. So in order to study this, what we do is that when the best fitness, the worst fitness and average fitness, they have converged, we stop at this point. By continuing a lot, you may have some slight modifications, you may not have some very big modifications, so we stop at this amount of time where best, worst and average they meet. When the best does not improve after high amount of time, it means some individual is high enough, it's trying by its limitation to move around, but still in all its location it is not able to find a good place. Then again we stop. Might means it has already reached its global minima, and irrespective of the convergence, it is moving about, it's not able to find out anything good. So again we stop. Some real-time systems, you need to give best solutions as per time. So we say 15 minutes, whatever best you give it. And that is where the iterative nature of the genetic algorithm, it comes into the picture. The solutions, they keep on improving along with time, along with generations. At any point of time you can stop and return the best solution. So far. Now we talked about global minima and local minima. The actual fitness landscape nobody has seen. Nobody knows what the actual fitness landscape for any problem is, and therefore there is no guarantee that we have converged into a global minima. By some kind of parametric modification, we can only hope that is a global minima, and we devise some techniques to escape from the local minima. Of course, when the number of local minima are too many, there are different techniques that we will work out together that we will see up to the later stages of the advanced sections of the course. But that is more or less what the entire paradigm of genetic algorithm is all about. That is what it's all about. This one especially relying on how you fix in the various parameters of the algorithm. This one, how you are able to fix in all the various parameters that we have got. So we continue with evolutionary computing. This is a part of it. This is of course the most fundamental part of it and the most essential part of it. The others lying the genetic programming, the evolutionary strategies, and some of swarm intelligence class of algorithms that you will be seeing later into the course. The immediate next point of discussion would be on the entire paradigm of the fuzzy sets, where we'll see how introduction of fuzziness and what is fuzziness, what role it plays, and then we'll build in another class of systems. We'll bring in another technique, we'll bring in another problem-solving tool that will be known as fuzzy inference system, and we'll solve some very exciting problems using this concept of fuzzy inference system into the next hour.